So what I'm going to do is I'm going to open this up a little more. Can everybody see that? Is that big enough? Okay. So now what we're going to do is we're going to talk about statistics. So this is basically a mathematical discipline that developed to determine whether two things were different. And the test that we're going to use to determine whether a certain team plays better at home or away is called a t-test. And this was developed in, I think it was the early 1900s, to determine whether beer in Ireland was better or worse the farther you put it away. I guarantee you this is a true story. So there was a statistician. So has everybody heard of the Guinness Brewery? It's in Ireland. World famous, probably the most famous beer in the world. And I realize you all can't drink, or at least not legally, but Guinness was is a big beer. And so what they wanted to know, but the thing is everybody loved the beer, but Guinness wouldn't ship it farther than, say, 50 miles from the brewery because they were afraid it would affect the quality of the beer so much that no one would drink it out there, that it would give them a bad name. So they wouldn't ship it anywhere, so everybody had to come in. But there was this outcry like, please give us beer, ship it. It's okay, we'll drink, kind of terrible Guinness beer. So the Guinness Brewery decided, well, let's figure out if we truly it has any difference. So there's all things you can to measure with beer. You can measure, carbonation, certain properties, how thick it is. So they got this statistician, I can't remember his name, but they said, hey, can you develop a test to determine whether our beer changes at all the farther we ship it out? So he basically developed this test I'm going to tell you today, which is called the t-test, or it's called the student's t-test. Because he developed the test and he was so, it was kind of slumming for him to work for a brewery. So he didn't want to use his real name, so he just put student's t-test and then published the results. And from now on, ever since then, it's always been known as a student's t-test. And again, it was developed to determine whether beer was better or not farther away. So this is the test we're going to use. We're going to use his test, his original test. But let's talk about distribution, though, right? Remember the human height thing? Yeah, we're going to review that. I figured that was a good thing. That we have a pretty good idea how tall people are. That not just individuals, but society in general. That if we look at height, and we'll see this on this other slide, you have a lot of people that are a certain height, kind of in the middle, and what happens is the amount of people at either end of that median, or mean, kind of drops off. You have less and less people. And this is kind of a representation. These are all women arranged by height. So the tallest ones are on the right, the shortest ones are on the left. And as you can see, most people kind of hang out in the middle. Does everybody see that? This is called normal distribution, where you have a trait or something you're measuring where you'll have an average kind of value for that, and everything kind of has kind of distributed to either side in equal volumes, and they decrease. So it's a bell curve. Everybody heard of the bell curve before? This is kind of where it evolved from. Bell curve. Okay? So we can think of this as like our scores too, right? That these teams, like when we take the average of these teams, a lot of times it's around 22, right? Or 20 or 19. Basically what we've done is we've created one of these bell curves for these scores. Is that, say it's, the correct score is 19, but the other team, this team might, has scores that are like, say, might be 0. Might have a score that's 45. It's just that it has more scores that are in the middle, so therefore we draw this curve like this around the data. Bell curve, very, very important. This is also called normal distribution or standard distribution. Normal, standard. Okay? Now, here's what I want you to think. Is this the only way that data can be kind of spread out over a particular trait? Think of another way. No, what I was thinking, basically what I'm saying is, you know, if like a team score, or let's say that if I'm measuring something, is the data always like that? Is that most of the data is in the middle around the average, and you get less and less number of observations the farther you go? Do you always get a nice bell curve? What else could you get, you think? Yes, bimodal. That's called bimodal. Or what about maybe you just have one peak? And so in that instance, you would have two peaks, right? Let me show you a picture of it. So in this one, this would be bimodal. You've got a high concentration at the low end, a lot of birds with a small beak, and a lot of birds kind of at this middle peak. So it's not this nice, curve here that goes down like this. You've got kind of two peaks. We can also have it skewed, right? And you can see why this bimodal. Say that all these birds are on this island, and you have two main types of flowers that it eats from, right? There's no kind of middle flower, so either the bird has to adapt to eating the small flower or the big flower, and you don't see a whole lot of birds in the middle. But the average beak size is probably somewhere in here. Does everybody see that? Even though there's hardly any birds at that. It's just you're taking the average of this. The other thing you can have, if you have one peak, it can be skewed. So that's skewed distribution. Standard distribution or normal distribution. You can have bimodal distribution or skewed distribution. And there's some other kind of variations on that, but you could think of, say, this one. Say we're doing the human height thing, right? And we're measuring women's height. And we end up at, for some reason we decide to measure all, girls in basketball, right? Which, again, we're going to we're going to find more girls that are taller than shorter, right? Or you would expect that. Again, this kind of skewed thing. We could do the same thing with men. Say we were looking at, horse jockeys. It's going to be skewed to the lower heights or the shorter heights. So again, a lot of the statistics we're going to do basically pretends that we are dealing with normal distribution. So let's look at this bell curve a little bit. Okay? So again, let me see if, hopefully it's probably going to cut out on me. I had a nice graphics where they fly in and you would see them like they come in here and there, but all right. Put that in your mind. Just picture all the colored things flying in. So the middle of this bell curve, let's talk about the bell curve a little bit. All right? So these are the values. The x-axis is going to be the values on this bell curve. So that if we were looking at, say, team score, right? The average score, say like, 22 points, would be right in the middle. Then, those teams, though, it wouldn't score 22 every time. There'd be a lot on the left side and the right side of that mean, lower and higher. But all of the values should be represented underneath the curve. So everything, the area of the curve or underneath this represents 100% of the data. Okay? And when we say the mean, that just represents 1 point of that data. Does that make sense? Okay. Now, and you're going to hear these terms a lot, and I'm going to introduce them. We're not really going to go into depth, but you're going to hear these a lot. If you take the middle 68% of this curve, that's called one standard deviation. Or on, 68% on either side is called one standard deviation. That's the spread. Remember, we were looking at the Broncos defense. Their spread was, if we turn this into the Broncos and the Green Bay defense, which hill would be skinnier? Broncos defense or Green Bay defense? No, they had the less wiggle. They were more variable, right? So they would have a wider hill. For Denver, because most of their data fell around the mean, right? Then it would be skinnier. And this is going to be important. Okay, and so this value here, the standard deviation, kind of gives you an idea of the spread of a data. The higher the standard deviation, the wider that hill is. Okay? You can go 2 standard deviations, and this corresponds to about, so if you went 2 standard deviations on either side, this corresponds to about 95% of all the data in this area that you're measuring. Does that make sense? We can also call this, and this is kind of a magic number, that's why I'm bringing up these terms, standard deviations. If you go 2 standard deviations on either side, that's called the 95% confidence interval. So if we were doing this, say, for the Broncos defense, I would give a number, say, from 17 to maybe, I don't know, I'm just making stuff up, to 24 would represent the 95% confidence interval. That means 95% of their games are going to fall into that area. Does that make sense? Okay. So again, confidence intervals are very important as well. Your standard deviation kind of gives you an idea how wide your data varies. The confidence interval tells you in this range, I expect to see 95% of my observations. Okay? Now we're also going to talk about these tails. These tails are very important. That if I go right outside my 95% confidence interval and I look at the data under this part of the curve, this represents 2.5% of my data. And you're going to find this is the edges of these kind of hills that we've created are going to be very important because we're going to use these to compare to other hills. Does that make sense? Okay. Let's take a look at that. And you all have seen this one here. I wish this thing worked. All right, I'm going to try this one more time. Now, I know it's going to mess something up. I'll just throw that down here. So again, here is, you guys have seen this before. I gave this to you last year. I'm sure you all remember, right? We're talking about human height, right? And we can divide it up into males and females, right? We can look at each one separately. Just like we look at scores, right? You know, you can have scores for the entire NFL, or you can just look at the scores from one team versus scores from another team, right? Here we're kind of doing the same. You can think of this as scores. So scores from the females, scores from the males. So based on this, and once we've constructed these hills based on our variables, we can answer very kind of cool questions. So what's the height? So it looks like the average height here is about 5'7". What's the height where if I called my buddy on the phone and he says, hey, I'm with somebody here, they're this height. No, actually, so if I call my buddy and he says, hey, I'm here with somebody, they're 5'7", what's the chances they could be male or female? Equal, 50-50, right? But now what if I call my same buddy and he goes, hey, I'm with somebody here who's 5'9". What are the chances of that person being a male or a female? 90. Yeah, because it's right there. Yeah, I know. But at least you saw it, right? Does everybody understand that? If you look at the area here, I mean, that's kind of what we're doing here. We basically turn numbers into hills, and then we see how much they overlap. And where they overlap is called the p-value. Okay? So in this instance, there's quite a bit of overlap here. What I would say is height is not a very good way of determining differences between the males and females, is what I would say. I would say the area, and basically the p-value represents the area under the curve where these two hills cross. Does that make sense? So this p-value here, I would say maybe, what do you think? 20%? 30%? maybe 30%, about that. Okay, in science, usually what we want is we want this p-value to say that certain things are truly different, really different. I want this p-value to be about probably 10% or less. And once we get that, so the p-value, when we start talking percents, we're going to look at p-values. They're going to be, percent equals 0.0, like 1% would be 0.01. So usually what you use, to determine differences, the gold standard in science is a p-value less than 0.05. So that means there's a 5% chance that these really are the same. But there's a 95% chance they're different. And that's what we look for. Okay, now we're going to do this with our football data. Okay, so let's go back to our spreadsheet.